Okay, so welcome back. I will continue where I stopped. Okay, so what we modeled this morning was a specific type of sequential social network where I modeled the formation of informational cascade. And now I'm going to look at, I'm looking at any type of network here where I have a group of agents and they are related. And as I said, the relation can be, so this is the signature of my models, agents, capital A. They are related. I call that relation F for friendship relation. There is a threshold, which is going to play a role when agents change their behavior. All agents have some atomic propositions that are true for them. And then there is some dynamic rules that tell me how agents change their behavior. As I said, these relations can have different properties, but I'm going to assume typically that they are going to be at least reflexive as well. All right, so instead of having a friendship relation, I can actually also replace that relation by a weighting function. And what would that weighting function do? So it's a function tau. And when I write tau AB, it would capture the strength of friendship or the relative weight that agent A attaches to her friend B, to her relationship with B. So it encodes a notion of trust. You can think of it as a degree of trust that A places in the information that she gets from B. And what you would want is that for an agent A, that all the sum of all the weights of her friendship with B, with all her friends B, would add up to 1. Now, in that case, what would be the reflexive relation mean? So tau AA, what does that mean? Well, it would capture somehow the trust that she places in her own likes that she puts on Facebook, right? So I have agents, they're related to their friends, or I can model that friendship using this weighted relation tau. Now, agents adopt new behavior. And when are they going to adopt new behavior? Well, their friendship is going to play a role. So, for instance, you would say they adopt a new behavior if the relative value of her friendship with all the Lady Gaga admirers, if that is the thing that we're after, is high enough, then you adopt that property as well. So this would be the case where you would want to model, for instance, I adopt a new behavior, like I will like Lady Gaga if B is my boyfriend, if tau 8B is bigger and bigger or equal than the threshold that I put there. Or the opposite could also happen. You have if the sum of the weights of all my friends can be everybody in my friendship circle will always be less than tau. This means I will never change my mind. I never adopt any new information. Now, a second way of looking at these models would be to go to neighborhood models. And that's the next thing that I'll do. So here I take an agent and I'm going to assign to every agent, yeah, you can see that, some family of sets of agents. And I call these the influential circles of friends that an agent has. And these are influential circles that an agent has because they are going to determine when an agent adopts new behavior. That's another more abstract way of looking at it. So how do the neighborhood models look like? So I've now replaced the friendship relation with a neighborhood function. So I have the set of agents, I have this neighborhood function, and I have a typical valuation that tells me which agents have which features in the model. What are the conditions that I put on the neighborhood function? So remember, the neighborhood function tells me who the influential circles are that an agent has. So which influential networks is she part of? And influentiality here means influential enough for her to adopt new behavior. So I'm assuming that all agents have at least one influential circle of friends. So N of A should not be empty. And there is a notion of monotonicity here, so that if agent A has an influential circle of friends B, and she has another friend C who's influential, then the union of B and C should be an influential circle of A as well. So should be included in N of A. And I put a consistency requirement that if agent A has two influential circles of friends, B and C, then they should overlap. So B and C should not be disjoint. So the intersection should not be empty. How do I motivate these conditions? Well, if you think back of my weighting function, then the influentiality condition, the first one, would correspond to saying that, well, all the relative weights that you put in your circle, in your influential circle, or on all your friends should add up to 1. The friendship restricted monotonicity condition would be kind of monotonicity within the group of all agents' friends. And the consistency condition, which required me that influential groups of friends, when they are really influential, should overlap, gives me consistency requirement for saying that I adopt new behavior when my threshold would be bigger than a half. And why is that? Well, you can think of the fact that if I have a group of friends B that influence me and they tell me to adopt P, and another group would be influential as well, and they go for not P, then I would have a problem, right? So then I would be stuck between P and not P. So this is the reason why we're requiring, in this case, a consistency condition to say that these groups, if they are influential enough to persuade me to adopt one of these things, they should overlap. There should be they should overlap indeed. In that setting, in these type of models, I now want to look at the formation of cascades, as we did this morning, but now not necessarily in a sequential network. So cascades form when agents follow their friends. So here, given a typically small group of initial adopters, so some fashion or proposition Q is going to be true somewhere, it's a new fashion. So then the application of my dynamic rule may give rise to a cascade. And that means that Q is going to spread throughout the network, a rapid expansion of the group of adopters of the property Q. Of course, these cascades may eventually reach a fixed point. So if it could be that everybody, the whole group of all the agents eventually adopt a new property Q. It can also be that at some point you enter into a network where things keep changing. Now everybody adopts Q and then they adopt not Q, Q, not Q. So it can be a more chaotic dynamics as well. If it reaches a fixed point, then that's what we call the extent of the cascades. And the extent of the cascade is the set of adopters, everybody who then adopts Q at the fixed point. So any new dynamic update of the model is then not going to change and make new people adopt Q. So then we have reached the fixed point, the extent of the cascade. A full cascade is those indeed when the whole set of agents, everybody has adopted the new fashion Q. Now let's see how these cascades form. So here I have put the threshold to be 2/3. And let's look. So I have a small network. I have red and blue nodes, and these are the only properties that agents can have. They can either be red or blue. So let's look at this red agent over here. Has 2 blue friends and 1 red friend. And that's enough for her to adopt the new behavior. So she's being influenced to become blue because my threshold is 2/3. So then look at the next red agent. So now when the first agent turned blue here in the corner, then that's enough to trigger the next red agent to become blue as well. So she turns blue. Then the last one is triggered by her friends. And then in her neighborhood, indeed, everybody was blue. So she becomes blue as well. We reach the full cascade, right? Now, an interesting question, which was asked in the literature: under what conditions does a certain fashion or opinion property that agents have produce a full cascade? This means that the whole group converges, everybody, all agents, unanimously to this new opinion. And the answer is that, well, this depends on the existence or inexistence of clusters of unadopters or disbelievers in the initial configuration. So we're looking for clusters of agents who can block the formation of a full cascade. And what is a cluster? So a cluster is a set of agents, a set G here of agents. They contain none of the initial initiators of the new fashion, if the new fashion is Q, so they don't yet have property Q, but they're such that every agent within that cluster will have 1 minus the threshold number of friends belonging to the same group G. So here I use the notation theta A for the adoption threshold for agent A's percent for her friends. So that definition and also the link to the cascades, I always refer to this book. That's the Networks, Crowds, and Markets book by Easley and Kleinberg, which describes this and also actually describes the Bayesian setting of the urn example that I previously presented this morning. Let's look at the example now when there is a cluster that is being part of it and that will block the formation of a full cascade. So now theta is here to take in, so my threshold for agents when they adopt, it's a uniform threshold for all the agents. I take it to be equal or bigger than a half. So look at the first agent, the red one in the corner. She's got, the majority of her friends is blue, so she adopts blue. The next one is going to look at her friends, adopts blue, etc. Until here, that agent in the third generation of my model was red. The majority of her friends are it's equal. She has equal amount of blue and red friends actually. So 2 blue and 2 red ones here. That's enough for her to become blue as well. So it triggers her to become blue, but none of the others are triggered anymore. So now there's a cluster of red ones that will never become blue. So this blocks the formation of the full cascade. And indeed, there is a theorem in that book, Networks, Crowds, and Markets, which tells me under which conditions a full cascade is formed and that cannot be formed or requires the absence of these specific clusters that can block the cascade. Now, what we were after is to reprove that theorem, or at least look at it in a simple way using logic. Because the proof of the theorem in the Networks, Crowds, and Markets book takes several pages. And what we saw is that if we encode certain features of the network in this logical setting, then actually the proof becomes extremely simple within the logical framework. So I will do that. So the logic looks as follows. So this is the language that I have here. So I have atomic sentences, negate, Boolean operators, classical negation, classical conjunction, and 2 modalities. I have a triangle phi modality and I have a diamond phi modality. And as before, so the type of models I'm having in the background are either the weighted semantics or the neighborhood semantics, which means properties are true and evaluated at agents. So agent A can have a property P. So I evaluate this very simple. So in this part, there is no epistemics or no sophisticated epistemics here. All the beliefs, if there would be beliefs or so, it's just atomic it's encoded as an atomic sentence. Now, what does my triangle phi mean here? Well, it's going to encode my influential circles of friends. So triangle phi means, in the weighted model, it will mean that the sum of all my friends would be bigger or equal than my threshold. It's like I have enough friends that have property phi for me to be influenced to adopt property phi. So that's what triangle means. So indeed, the number of A's, I'm evaluating this for the agent A. So it's A's friends is bigger or equal than her threshold, theta A. There is a classical dual for this triangle, which is the nabla modality. And the nabla modality would then have a meaning such as, well, it's significant enough for you to prevent adopting the opposite. So not triangle, not phi, right? So prevents, it would be a significant amount of people that prevent you from adopting not phi. In my language, I have a diamond modality, and the diamond also has a dual, which would be the box modality. And what does it mean? So the semantics I have for the diamond modality means that I have one friend, or at least one friend has property phi. So there exists an agent B who is a friend of agent A, and agent B has property phi. So it's just saying, okay, agent A has a friend who has property phi. And the dual of the diamond, so not diamond, not phi, would then be the way that I define box phi. And box phi just means all of my friends have property phi. So you see, I have a language where I can express two things. Some agents have property phi, so some of my neighbors have phi, all of my neighbors have phi, or I can say enough of my neighbors have property phi to influence me to adopt it as well. I'm assuming here to be reflexive. Yeah. So that's a design choice that you can make depending on if you really want to model real friendship or informational access. But for most of the part, I'm thinking about informational access. I can access my Facebook posts, I can access your Facebook posts, etc. So that's the informational access meaning of friendship that I have here. Now, if you look at these modalities, then you see that, well, the diamond and box modality for some, I have some friend who has phi, or all my friends have phi. They are normal existential universal Kripke modalities. And they're similar to many modalities studied in the literature, but the triangle and the nabla modality are not normal modalities. But they do have a feature. They are monotonic modalities. So what is the case is that if phi implies psi, then it is the case that triangle phi implies triangle psi. So they behave in a monotonic way, which is interesting because even if they're non-normal modalities, they do have very interesting features that allows us to do many things with it in a logical set. Here I have written down the semantic meaning of triangle using the neighborhood semantics. The neighborhood semantics is very simple indeed. Remember, it's a set of agents, neighborhood function, and evaluation. And the neighborhood function gives me for every agent the circles of friends that are influential for her. So the triangle phi in that semantics means just that there exists an influential circle of friends, all of whom in that circle of friends B have property phi. And some agent A has some friend who has property phi, just means there exists an influential circle, capital B, one agent in it, small b, has property phi. Right, so now we can actually, given the conditions that I had on the neighborhood map for in the neighborhood semantics, we can actually provide a sound and complete system axiomatization for this logic to reason about these modalities. Enough of my friends have property phi, or all of my friends have property phi. I quickly go over this. So how does the system look like? I have all propositional tautologies and modus ponens, so classical. Box is a normal modality, so I would have the necessitation axiom, which says that from phi I can infer box phi. Kripke's distribution axiom for the basic epistemic model logic system, for instance, would also have this. So it says that box phi implies psi implies box phi implies box psi. And then the conditions that I had from before, which would say that the neighborhood function should be non-empty. The overlapping of two neighborhood or influential circles should also be non-empty. And a monotonicity requirement. So I encode this in this way. If all of my friends have phi, so box phi is true, then that implies phi is true, which captures the reflexivity of the condition here. And if all of my friends have phi, then that implies triangle phi. It means that I have an influential enough circle of friends that have phi. And if I have two influential enough circles of friends, one promotes phi and the other promotes psi, that implies that there exists one friend that promotes phi and psi, which means that the two friendship circles have to overlap. So that's the condition that matches that. And indeed, the monotonicity condition that I already mentioned, phi implies psi, and triangle phi has to imply triangle psi. Now, let's look at what happens when the model changes. So the dynamic change of the model when agents adopt new features. So an initial feature Q is true somewhere in the network, and then the model keeps changing. You're being influenced by enough of your friends so that then in the next stage you can adopt Q as well. So in order to do that, I'm going to extend the logic with a fixed point formula. And that leads me to a neighborhood-based type of new calculus. And why is that good? Because what it adds to model logic is that now I can talk about self-referential or circular definitions, which are actually interesting when I want to talk about the formation of this cascade. Because the cascade of the network is kind of a fixed point where everybody has adopted Q, the initial behavior, and from then, that moment onwards, Q doesn't change anymore. So these fixed points are going to be important when I want to express that in the model logic, then mu calculus is going to be very relevant. Also because my triangle modality is a monotonic modality, not a normal one, but a monotonic modality. So this means mu calculus is actually well defined for monotonic modalities. Let me tell you a little bit about how we reason about fixed point logics. So there is a thing that we call the smallest fixed point formula. So here agent A satisfies this formula nu P, Q, or diamond P. And that means that if A belongs to the smallest set of agents, capital P, which satisfies this self-referential equation. So this captures the circle of Q adopters. So either you already have property Q, or there is somebody, a friend, who is going to, and then P, and it's recursive, so then has property Q as well. Now, so that is the smallest fixed point formula that I express. And then the largest fixed point formula would capture somehow the set of the Q fanatics. So that's nu P dot Q and box P. So we'd say that either you are a Q adopter and all of your friends, so box means everybody in your circle, all your friends, and then P, we go back, are Q adopters, right? So these are the agents whose social circle consists only of these Q adopters. So either you're Q already and everybody that you have will be Q as well. So this mu calculus extension of the neighborhood logic is decidable and completely axiomatized by adding the axioms of standard mu calculus rules to this setting, which I didn't spell out. But these formulas are important because they can help me to capture a few of these notions that are interesting in this context of modeling cascades and social networks. Namely, this formula here can capture the extent of the cascade, which is started by the Q initiators. So either Q is the case or enough of my friends. So now I use the triangle modality to capture my influential circle of friends, have property Q, and this goes on. And the largest cluster, which is the cluster that blocks the formation of the full cascade, would be the ones in which either not Q is already the case, and then it should be significant enough to prevent me from adopting Q. So nabla P, where P then gets back to this formula. So now I have a way using these fixed point formulas to express the extent of the cascade by initial adopters and also the largest clusters. That leads me to the theorem, which says that the formation of the full cascade depends on the absence of these specific clusters that block it, not as done in the network Schuyler Markets book, where this is a theorem that requires a lengthy proof, but here it actually boils down to just this tautology in mu calculus. So this tautology here expresses that the extent of the cascade is going to be equal to the complement of the largest cluster. So we're indeed, so having these fixed point formulas allows me to really capture exactly that, that theorem within the model logic setting. So which is one of the added values of using that fixed point logic here. Now, of course, the formula that I had there can trigger, so the triangle P or triangle Q that I have tells me that I have an influential circle of friends that is influential enough for me to adopt Q in the next round. But I mean, things might actually be easier if I just talk about the full extent of the cascade as I'm doing here. So I don't necessarily have to talk about what happens at the next round. The fixed point formula allows me to jump directly to what happens in the full, in one go to the formation of a full cascade. So I don't really need full mu calculus to this, but just an infinitary cascade modality, which is this fixed point formula here, which says that either I adopt phi or everybody eventually is going to adopt phi. And I write it as the infinite modality for the influence modality for phi. In addition, you can add the standard master modality for mu calculus to this, which is the triangle star phi. And instead of triangle here, I just have diamond phi. Right? So it's the fixed point formula with the diamond modality, which says that I have at least one friend that has property phi. Yeah. So maybe I'm not going to go over the full details of this, but I mean, with these two modalities, jumping in one step to the formation of the full cascade, and with this master modality, the axiomatization becomes simpler by just adding the standard fixed point axioms and rules that you have of mu calculus to this system. But I'll go a bit faster over that so that I can also talk about the network change at some point. Now, you can say, oh, that's nice, but you're jumping in one step to the formation of the full cascade, and you can encode that theorem when a cascade is full in the network. But maybe it's better to consider one-step adoption rules. So how people change their fashion as the network changes step by step. How can you model that? Well, we do that in the same way as we did this morning, using the methods of dynamic epistemic logic. So I go from an initial network model to a model at the next step, and I call that the new model M prime. And what can change here for now is just the valuation of the formulas. So I only have two ingredients in this model, the network or the propositional values that the agents have. And when they adopt a new fashion, it just means that I do a valuation change or an update. And I can do that by just doing a substitution. I can take the formula, either I already have property P or enough of my friends have property P to be enough for a trigger for me to adopt property P at the next step. Right? So I can introduce an adopt operator in the language, a dynamic modality, which I will now call adopt phi, When is adopt phi true for an agent in a given model? Well, when at the next step, indeed, agent A has adopted agent phi. And what is the law that regulates it? Well, it will mean, and I've written it here as a substitution. So adopt phi is going to be true if and only if within phi we're substituting this formula P is true, or I have enough friends that have property P at the next step by property P. So this is just the result of the uniform substitution of all occurrences in the network where agents either already adopted or they have enough friends that have property P. Okay, so step-by-step dynamics is easy to model in this way using this update rule where in this case just the valuation is going to change. When you know when that has to happen, well, when enough people have in your neighborhood have property phi. So that is easy. Let's add some epistemics to this now. So now let's add a knowledge modality to this language. So this is the language that I had from before, classical negation, classical conjunction. I can talk about some friend has property phi, enough of my friends have property phi, and now I add that agents know something about property phi. This is a variation of some work that was done in the literature by Patrick Girard, Fenrong Liu, and Jeremy Seligman. So they have some of the initial papers on it. One is called the Facebook friendship logic, where they also, in their setting, they actually have a hybrid logic setting where they use nominals to talk exactly about in the language, have very specific expressive power to talk about the agents themselves. How do the models with the epistemic information look like? Well, they're going to be a little bit more complicated than just the network models, because in addition to just having the agents, nodes on my network with relations, however I want to encode the relations, now I need to talk about the knowledge of the agents. And to do that, one way, I mean, there are probably many ways in which you can do it, but one way would be I have several possible worlds, agents, and I call the set of states of possible worlds is S. So worlds are W, S, T. I still have my set of agents, A, B, C, D, and all these agents have some propositional property that is true. So this is my set of atomic sentences of fashions that are true. Now the agents have indistinguishability relations, which I take to be equivalence relations over the set of states. And within every set of states, there is going to be a social network. So we're going to depict this as possible worlds in which either my friend has property P in this possible world, and in that possible world, my friend does not have property P, but I don't know it. So I have uncertainty over possible worlds as an uncertainty relation between the worlds. And within these worlds, I encode full networks. So it's if you actually want to implement it and model it, it's going to be complicated to do so, because now you have a two-dimensional setting in which you have both the social structure and you have the full epistemic structure. The models come, of course, with a valuation map associating with each fashion. Now, both the world in which we are evaluating it has to be specified, and then tells me the set of agents that have that property in a specific world. So the valuation map will come with a sub-index W for the world in which I'm evaluating it. And then either I work in the neighborhood models, as on this slide. And so then instead of the friendship relation, I will have a neighborhood map. The neighborhood map, as would be the friendship relation, would also be world dependent. Somebody can be a friend of me in this world and maybe not a friend of me in another world, and I might not know if that is the case. I might access your Facebook page in one world and not in the other one, and I might have uncertainty between those two worlds. So there are a number of conditions that you would want to put on this, reasonable conditions. So for instance, well, all these epistemic relations are going to be equivalence relations. The influence map, so the neighborhood function, satisfies the conditions that I had from before: influentiality, this monotonicity condition, and consistency. But now there is an interplay between the epistemic relation and the social structure of the model. So for instance, you would want to impose that agents know who their friends are, or they would at least know their influential groups of friends. So if two worlds are indistinguishable for an agent A, then that would mean that she has the same influential group of friends in world S as she would have in world W. That would capture the fact indeed that these agents know who their friends are, or their influential circle of friends are. If you don't want to model situations in which that is the case, of course, then you can change that condition. Another reasonable requirement would be to say that agents would know their own feature, their own property, their own behavior. So for two worlds that are indistinguishable for an agent A, if she adopts herself property P, or she has red shoes in world S, then we also want her to have red shoes in world W, if she cannot distinguish between them. In these models, the semantics of the diamond and the triangle modalities that I had from before is similar as the semantics that we had earlier, except everything now, so the social relation is going to be world dependent. I'm evaluating things for an agent at a certain possible world. So all the N's or the F's that I'm using here will all be world dependent. And what is the K modality? Well, the K modality is actually how I started the tutorial this morning, is going to be the Kripke modality for the equivalence relation. And the equivalence relation here is defined as the equivalence relation over the possible worlds. So I'm evaluating at a world for an agent, say that agent A knows that phi is the case. Well, if that is the case in all worlds that are indistinguishable for her, so all these worlds as indistinguishable from W would have to satisfy phi. So what is if you have the epistemic information, then it would be good to use it also for the way that the agents adopt new features. So the natural adoption rule in that context would be that you require agents not just to adopt new behavior when enough of their friends have it. So diamond, triangle P would be enough of her friends have property P, but you would require that the agent actually knows that that is the case. So we plug in an epistemic modality in front of triangle P. We'd say that either she already adopted P, or if she knows that enough of her friends have adopted P, then that is enough for her at the next round to adopt property P. The way the model change would be exactly the same as before, that indeed, in addition, of course, now the substitution would be that you take the K modality into account. So I've started with an initial model M, which is the model given at a certain moment in time, and you go into a new network model, which is an epistemic model, so they both have the equivalence relations for all the agents. And what you change again is the valuation. So an agent in the new model with the valuation prime, so primes are the new models at the next point in time, adopts property P when P is true, or indeed she knows that enough of her friends have property P. Now, the dynamic modality that you have for that epistemic case is very similar as the dynamic modality that we had from before. Adopt phi is going to be true at a point in the network for a certain agent, if indeed in the new model, in the updated model M prime, phi is the case. Now, one thing that we did in our paper, and this is just a small thing that I'm going to tell about it, there's much more to say, is that actually, when you have the epistemic ingredient in these networks, there is much more that you can do than just saying, oh, I know that all my friends are adopting something now, and then I'm going to adopt it myself at the next step. The epistemics can actually be used to speed up the way that the information flows within the network. And this is something that we have called foresight. That's because agents can anticipate it, they can predict that enough of their friends are going to adopt in the long run a feature file. And if you're fully sure that everybody is going to buy that new iPhone tomorrow, then you better be the first one already to be in line in front of the shop to buy it then. If indeed you're being influenced by all your friends who adopt this new fashion, right? So the epistemic ingredient allows you to do anticipation or to prediction of like how features in the network, because they have knowledge about their friends and their adoption behavior of their friends. They know, in this case, also the topology of the network. If they know that everybody is going to adopt a new fashion, they know that they will be influenced, then they can adopt it themselves right now. So this means that the foresight adoption rule is going to be a slightly different one. And so if we can model the full extent of the cascade, which I've done with this fixed point formula, then I can use that fixed point formula now in my substitution rule to say when an agent is going to adopt at the next stage. So given a model M and a model M prime, that is the new model, then what is going to happen? When is the valuation going to change for an agent so that she adopts property P? Well, this is going to happen when either she already had property P or she knows that enough of her friends are adopting P, but here I've plugged in the fixed point formula. So that's the full extent of the cascade that they eventually are going to adopt P, then she will adopt it now. So indeed, this foresight or prediction update rule is something that epistemics makes it possible to model these cases and of course, there are many assumptions about what they should know about the behavior of their friends, etc., that are built in here, but it allows the cascades to speed up. Now, that's what I wanted. So I have references in the end that refer to the papers where we are fully modeling this. And now I want to still tell you a little bit about a last part of work that I did with Fernando Velasquez Quesada on changing the network structure. And I have to look at the time. We're still in time. I can't tell you everything that I had prepared for this because that's requiring much more time. But I can tell you a little bit of what we did. So, okay. If you want to model not only how the features spread or the properties that agents, the fashions that agents have within the network, but also you want to look at how new friendship relations are being formed or how the network topology itself is changing, that would require a new dynamic rule. And you would have to determine in advance to say what is required for two agents to become friends. And in this case, what we did was we work with a new threshold, which I call alpha here, and it's a dissimilarity threshold. And it will tell me that an agent's new circle or new friends will be all those agents that differ in at most alpha features. So they should be similar enough to you to become your friends. It's also related to what is studied in the social science literature under the chapter of homophily, where you become typically similar as your friends, but you are also being influenced by your friends on the basis of similarity. So we use a threshold here to trigger when agents add other agents to their social circle, depending on how similar they are. How do I measure similarity here? Well, I don't have a lot of ingredients in these models, but the agents have propositional sentences that are true for each one of them. So I just use these propositional sentences that are true, and I check the similarity between the sets of features that agents have. If you do that, then you can start combining the two dynamic rules. So one is the one in which I adopt a new feature at the next round, and the other is when I'm changing the network structure at the next round. So I can combine two types of dynamics. And another thing that you can do in this case, which is also fun, is to say, well, maybe agents have a limit on how many friends that they can add to their social circle. So you can put a size on the maximum number that agents could have, which is something that we've modeled. Let me tell you a little bit about how these updates work, and then I will have to come to the end of the tutorial. So here I have a social network just as before. I have agents, they have friends, there's a friendship relation. But now a different type of threshold is the threshold alpha that tells me when agents are similar or not similar, an evaluation map. And then what you want is to, in the language, to determine how similar agents are given the set of propositional formulas that are the case. So I determine this using a formula, I call it mismatch between A and B, is the set of all atomic sentences minus the set of sentences on which they are the same. So all those P's that A has property P, if and only if B has property P. That allows me to determine the mismatch between A and B. And that exactly, of course, I have to make sure that that mismatch is going to be less or equal than alpha to trigger adding a new friend to my social network. You can take the cardinality of that mismatch set, and that will give you a number. It's the distance between two agents A and B. That distance has a number of properties. So that distance should be a non-negative number. The distance of A to A will always be 0. The distance of A to C, it's sub-additive, should be less or equal than the distance from A to B and the distance from B to C. Symmetric, distance from A to B and the distance from B to A should be the same. Now, these properties will then determine, so if my social relation in the future is going to be determined by this notion of distance that I introduce, then the features of the relation are going to be inheriting the features of this distance semi-metric that I introduce here. So the social relation is going to be a reflexive social relation, and it's going to be a symmetric social relation. So depending on what notion of distance that you use here, because there are many choices, that will give you certain features, and those are the features that determine how your social network is going to look like. Right, so let me maybe just say that, so what we did here, for instance, is that given a certain social network model, but without epistemics, agents, friendship relation, and this alpha threshold, then after the similarity update, so you look at whose agents are closest to you, then you would say, well, the new network at the next stage of my update rule would be the set of agents, the model consisting of the same set of agents, but with a new social relation. So now F is changed. How is F changed? Well, I form new relations only when the distance between, for any two agents, they're going to be related when the distance between A and B is less or equal than alpha. And it's based on the distance that I just introduced, the cardinality of the mismatch set of properties that they have. You see that this relation of F inherits the features of the metric of the distance that I just introduced. So indeed, that relation is going to be reflexive and symmetric. Mm-hmm. Now, there are many more things that you can, now we know how to change the valuation function. I can update the features that agents have. I can update the social relation. Then it is possible to combine these. In this case, also, you could add epistemic ingredients, which is another thing that we did. So I can add the epistemic relation to this model, so that I can require, for instance, that I'm only going to add you as my friend to my social network when actually I know that the features between you and me are not, the distance is less or equal than alpha. So not just that this holds, but I should actually require that the agents know that that is the case. All right, so I have more here, but I actually want to round up and to leave some time for questions here. So I actually jump directly to the end. Okay, so one thing that is interesting, and that's indeed the thing that I referred to as homophily, that is studied in the social network theory books. So homophily, in the Networks, Crowds, and Market book, when they mention this, they refer to the interplay between network change and social influence. So you need two ways in which the model can change, and that interplay is crucial for that study. What do they say? What is homophily according to him? It's the property observed in networks which say that agents tend to be similar to them, to their friends. Because if you compare your friends to a random selected set of agents from the general population, then you typically observe a big level of homogeneity. And indeed, these two processes in this case, so being influenced by your friends or seek friendship among people that are similar enough to you, are two dual processes. And both are important in that study of homophily. Why are the social scientists so interested in it? Because if you know the cause of homophily, then you can design measures to intervene certain diseases or certain things that seem to happen in certain communities. Okay, so there is one paper of the many papers with Fernando, which really captures the interplay between the two types of dynamic ways in which the models in the social networks change. And what I can say as conclusion is that these logics and variations of it are applied to the study of a number of social phenomena. So homophily already mentioned, but also the formation or prediction of polarization. And then you can check how far a model is from being polarized. The formation of echo chambers, informational cascades is one thing that I extensively talked about. And for depending on the social situation we're modeling, you want different design choices to be made. For instance, for part of the tutorial, I took the thresholds theta or the threshold alpha to be a uniform given threshold for all agents, but you can change that. It can be agent-dependent threshold. Everybody has a different trigger for when they adopt a new behavior. I didn't talk so much about giving up behavior, but just adopting new behavior, so adding new features. But of course, in more complex situations, agents also unadopt behavior. There are different ways in which social matching or the formation of new friends or social circles happens. The similarity-based one, the similarity distance that I here had introduced, is only one way of doing it. There are many other ways in which you can say that, maybe people have to be complementary to each other for a new friendship to be formed. And then there are different properties of the social relations. Different epistemic attitudes can be added. All the epistemic attitudes that I modeled here were notions of knowledge that are based on equivalence relations. So these are S5 notions of knowledge, which are very, very strong notions of knowledge. But of course, from the philosophical literature, we know that there's a variety of weaker ones. And another property that we studied in the social network literature side with the social network models is the triadic closure condition, where in order for two people to become friends, there has to be maybe a middleman or another agent who introduces two agents to become friends. So then again, the epistemics plays a role because you want the middleman to know two agents and those agents introduce two agents to become friends. So it's a more complicated way of forming the new social networks. And then I have the references here, so a whole series of papers, and there are more on my website. So thank you.
Are there any questions from the audience? I have one question. So I would like to know how easy it is to model, to actually model the fact that some properties are mutually exclusive one the other, to some way to simulate the fact that maybe a facial goes through different states in this sequence.
So you're after, I mean, in the logical setting, that is very, given just the propositional logic that I here have, given these conditions, that is just a syntactic encoding, which is very easy to do, right? But it, of course, depends if you are, if you're thinking about a full implementation of these networks in reality, where I have huge networks and then I want to change the network step by step, and I want, in addition to the social network, also the epistemic models to be there. Then, I mean, the problem that we have with actual implementation of these things is that, of course, when the network size grows, then this might not be the right tool. I mean, this helps me to reason about these models, but to actually encode and implement these things for a huge size of networks, then you might not want to do that in this way. I think that's not going to be practically feasible. The other problem that I was talking earlier with other people is that when there is certain, here the networks just, the size of the set of agents or the size of the network in the terms of how many nodes you have is fixed. But of course, you could also say, oh, my set of agents is going to grow, or which happens in case you model the epistemic ingredients, which is actually the added value of having the epistemic ingredients on top of the social relation here. As we saw this morning, these models, they can really, every time an event happens, then the state space grows. So implementing that is going to cause problems. Of course, there are ways around it. So one of our colleagues at the Institute has found a way of having a nice syntactic encoding of how to model that so that the state space doesn't, every time you do a dynamic thing, that the model doesn't blow up. So it doesn't exponentially get bigger and bigger and bigger, which would be. But if it's just an encoding of a mutually exclusive set of properties in a logical formula, then that is easy to do. But of course, if we're talking about actual implementation, then there are, I think, other things that would make that more difficult.
That's very clear. Thanks. So again, I invite new questions.
There was also a question there.
Thank you. About the combination of these two updates described, updating the network based on similarity and updating the properties of the agents based on what their neighbors. If you combine the two, updating the characteristics of the neighbor influence the distance, and that may be indirect. So
yeah.
Exactly. Study them in combination that we look together also guarantees that regardless of all of the performed operations, when life in same situations in order to get straight long-term multiplier conditions.
Well, I mean, we have like one paper where we mention it. We started looking at these features, but those are not fully explored. I know that the team in Groningen has also looked at this, and you're fully right. So the order in which you perform the dynamic updates is going to matter and can completely disrupt things. So some features that may be interesting is yeah, but these are like complete disconnected subparts of the network. So you have some notion of segregation or separation of the network. Okay, so it depends. Some clusters or some things might stay stable, but I mean, yeah, working that out is still work in progress. So we didn't do that, but there will be certain features that will be stable no matter what type of updates that you're going to do. But yeah, in general, the networks are not nicely going to be behaved, and all kinds of behavior is going to appear. So you have to really make certain conditions of the order in which you do the updates and what type of updates. But we didn't really study those features yet in full detail. No, we know that to study homophily, you need both types, but if you actually implement it, then many of the properties are going to be messed up. That is correct.